Okay, now we're live. Um, is there another problem you'd like to look at?
I couldn't figure out 35.
All right, let's look at 35.
Well, what I got didn't match the answer in the back of the book, so I mean, or I didn't really understand what they were saying about the answer in the back.
Yeah. Okay. So here we go. 35.
35.
So this part, let's see. So this is the part. Let me get my pen going here. Above the line, that's what's in the book.
Mm-hmm.
Okay. So now what you got to do is observe patterns. What's going on the left side of the equal sign? We'll get the right side later. The first line is just 1 squared. It is 1 plus 2 squared.
Okay.
The third line, plus 3 squared. Do you see the pattern?
Yes.
Add another number inside the square sign. So as you can see, my new next line is 1 plus 2 plus 3 plus 4. All of that is squared. Okay, so now on the right side, I guess that pattern is really simple. 1 cubed plus 2 cubed, 1 cubed. So you just add another number cubed, right?
Right.
So, all right. So let me go back to the problem now. What are the next 3 lines? So that's the first line. Okay. And you didn't have to do that number. I wrote down, see, I actually calculated it out to see if it really worked. Isn't that a curious problem? You know, what's 1 plus 2 plus 3 plus 4? 3, 6, 10. And what's 10 times 10? 100.
Mm-hmm.
1 times 1 times 1? 1. 2 times 2 times 2? 8. 3 times 3 times 3? 27. Mm-hmm. 4 times 4. And if you add those up, do they really equal 100? They do. So anyway, it works. What would be the next line?
Okay. Well, I was getting 102 on the other side. Maybe I just added wrong. But it was the same for all. I was just two more on the right than on the left. I got 100 on the left side.
They're equal. 1 plus 8 is 9. 9 plus 27 is 36. And 36 plus 64 is 100. So they really do.
Okay.
Maybe you didn't have those numbers, but anyway, it does work.
Okay.
So what's the second? So this is just the first line. The second line, well, just add another number. So I threw a 5 in there and squared it. What's the right side going to be? 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. And I'm not going to do the third one, but anyway, you were supposed to do the third one too. Mm-hmm. What does the pattern suggest? Well, yeah. So it says, what does the pattern suggest? So the pattern suggests that if you add up a bunch of numbers and square them, that's the same as taking each individual number and cubing it to the third power and adding them up. So just kind of putting in words what the pattern is showing. Yeah. Follow-up questions? Okay. So again, it's discovering the pattern and then you kind of extending it. I didn't do that third one, but I mean, that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6, parentheses squared. On the right side, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed. So just extending the pattern. Other questions? Okay, well, let's get on to this this lesson that we were gonna this new. I'll give you guys another chance. Did anybody still have a question they wanted to ask?
Nope.
Okay, so this is just a little bit of a what I guess you could say a post note on the lesson we had last time. Article in a magazine. I mean, if you think this isn't math or this isn't very powerful, finding pattern searching, this article points out that pattern matching is actually one way of catching terrorists. So it's incredibly valuable. And anyway, that's it. Just that comment. Okay, then I wanted to tell you this little story from math history. A famous mathematician by the name of Carl Gauss. He's in grade school, and you could just see, I could just see it. His teacher obviously must have had a headache or something. And he says to the kids, maybe they were making too much racket, I don't know. And he says to the kids, all right, I just want you all to quiet down. I want you to sit down, and on your paper, I want you to add up the numbers from 1 to 100. Go. 1 to 100, total. And after about 2 seconds, Carl puts his hand up. Ooh, 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 ooh. Carl, I told you to add up the numbers 1 to 100. I've got an answer, sir. Well, he's not, he didn't just have it in his head, but here, I want to show you what he did. It's really clever. So what I'm going to do is write on the right side here and just show you. So he grabbed my pen. He said, all right, if we on one list, let's just write the numbers 1 to 100. I'm not going to write them all out, but let's just write them in order from 1 down to 100. Get down to 100. And on the right side, make another list, this time count backwards. Whoops. Okay, so if you make those complete lists, the two lists would look like that. And then he noticed, look at the total of the first row is 101. The total of the second row is 101. The total of every row is 101. Oh, well then couldn't I just take 1 to 100 and multiply it by 101? Yeah. And then the answer is just what? How do you multiply by 100? You just put a couple zeros on the end. Except what's the problem? He's got two lists, so he's got to divide that in half. Oh. So anyway, the point is, that's what Carl came up with, and of course that is exactly correct. That doesn't, I'm not trying to show you how brilliant he was, even though he was, but the idea here is he just did it with patterns. Anyway, pattern matching can be incredibly powerful. So that's the only reason I brought that example up. Okay, so remember last time we told you that the lesson 1.1 was in chapter 2? Well, now we're going to continue. And this time we're actually going to take a lesson from chapter 2. The lesson title is at the top there. Sets, a problem-solving tool. And of course, that's in the book too. And then what I've got, what I put on there for pictures is just what? Oh, what I thought were common sets of things. A set of golf clubs, a set of dishes, a chess set, a set of cards, a set of baseball cards, a set of tickets, and a tool set. Pretty common. I mean, we use sets all the time. Okay, so that's kind of what we're getting into in chapter 2. Okay. Now, you don't have to write these down, but let me just go through these fairly quickly. Here's pretty much what we're going to do. We're going to tell if a set is well defined or not, and that's actually pretty easy to do. And if somebody says, for example, the set of all tall people in the first row of the class. That's really badly defined. What do you think is the problem with that? What if I said, oh, it's a set of all of you in the first row that are tall? What's the problem with that statement?
Your definition of tall.
Yeah, exactly. I haven't said what tall is. Okay. And all right. So anyway, that like you said, you can determine that pretty quickly. In part B, we're going to describe a set in words by listing. We're going to also do it by listing its elements, and we're going to use something new called set builder notation. Third, we're going to determine if two sets are equal. Fourth, we're going to find the number of subsets a set has. And then for the last part E there, I'm changing it a little bit. The book wants you to learn the RSTUV procedure. RSTUV has 5 letters, so they've got a 5-step process. Mine is only 3. So I simplified it. So anyway, that's where we're headed. So there's a lot of things here, and let's get started. So first of all, what's a set? It's just a group of things, a group of objects. I mean, that's pretty obvious. What is important is, in sets, we never list multiples. So, for example, if you had a set of baseball cards, I know they don't really have those anymore, but when I was growing up, boy, that was all the rage, having a card for each player. I don't know, maybe they do that. I've been away from that too long. But anyway, so you got a set of cards. So what do you do if you've got 2 of one player? Well, in sets, we never list multiples. So that's what I listed here in this second spot there. Multiples are not listed. Elements are not repeated. You'll see that in just a minute. So here's an example of a listing. A listing. Set A has the numbers 1, 2, 3. Continue the pattern until you get through 10. So in other words, set A is the numbers 1 through 10. So we can just write a listing. In this case, I even took a shortcut because the pattern continued. Do I have to keep writing out 4, 5, 6, 7, 8, 9? No. If the pattern is established by 3, I can tell it just continue, ... Oh, and by the way, you have to put the last number down. Yeah. Okay. Verbal. That's just putting that set on the top in words, all counting numbers from 1 through 10. And here's the one that it's going to take you a little while to adjust to, number 3, called set builder notation. So you've got this x/x is a counting number. 1 is greater than or equal to 1, which is less than or equal to 10. And we got, okay. And by the way, I do have to apologize. My brackets are really lame looking. I'm really bad at drawing brackets. So anyway, my apologies in advance for that. Now, here's what this reads. This reads all x such that x is a counting number and x is between 1 and 10. So all x such that, I wrote it down in the bottom, the x/x, means all x such that, and then the other x. Now, you're probably wondering, why do we have that number 3? And the answer is, you can't, some sets we have no other way of doing. You'd be stuck if you didn't have that. So all x such that x is a counting number, and then this just says x is greater than or equal to 1, and it's less than or equal to, in other words, it's all the numbers from 1 through, all the counting numbers from 1 through 10. Well, we're going to have to get used to that. All right. Let me just show you an example of where you need set builder notation. Okay? So if you were describing the set of natural numbers, that's just up here at the top. That's just this 1, 2, 3, going on forever. In other words, all the whole numbers, 1, 2, 3, 4, 5, 6, going on forever. Okay? That's just called a listing. Okay. The whole numbers are 0, going on forever. The integers are the negatives and the positives. We don't need set builder notation there, but when you get to the set of rational numbers, you can't do it unless you use set builder notation. Here, the set of irrational numbers. You know, how else could you write? What that means is, list for me all the fractions. Well, you can't say like 1 over 1, 2 over 1, 3 over 1, because what about 1 over 2, 1 over 3, 2 over 3? There's no system for organizing and putting them in a list. So instead, on the right, circled in black, there's set builder notation. And it says, all x such that x is a divided by b, where a and b are integers. So divide one integer by another. Oh, and by the way, the bottom number b can't be 0. There is just no other way. Anyway, you don't have to remember that. That's just an example. What I'm trying to tell you is, some sets, you cannot describe them unless you use set builder notation. You don't have to remember the set of rational numbers. That's just my example. Okay. So we'll get into that in a little while, but now some important sets. First of all, there's something called the empty set, also called the null set. And it's simply the set with nothing in it. So you notice bracket, bracket with nothing in between. That's called the empty set. In German, you know, if somebody called you a Nullkopf, that would be their way. They would be calling you an empty head. This is also called the null set. So anyway, this empty set has no numbers in it, nothing. Okay, what are equal sets? Equal sets are two sets that have the same contents. If you look at this example, would you agree that sets A and B have the same contents?
Yes.
Yeah, so to be equal, they don't have to be in the same order, do they?
No.
Yeah, just so they have the same numbers in them. So you see A has 1, 2, 3. Hey, B has 1, 2, 3 also. Therefore, A equals B. All right. Next, we have subsets. So these are three examples. You don't have, you don't have to write this all down, by the way. I think you're aware these slides are available on the webpage.
Mm-hmm. Yeah.
Okay, so you don't have. I know I see people slaving away there, and that's okay. But that was my mistake. You don't have to write everything down. Just try to get the concept. So here are three sets. A is the numbers 1 through 10. B has the numbers 2 and 7. D has the numbers 0 and 1. Okay? Now, we say B is a subset of A. And by the way, this big fat horseshoe opening to the right stands for is a subset of. You're wondering why I made the C over. So that's really not a C. It's literally like a horseshoe, and it's open to the right. That stands for B is a subset of A. Now, what do you think that means?
They have the same element or some of the same elements.
Yeah, all of the elements in B are also in A. Yep. It's like a part of A. All right. How about D? Sets the numbers 0 and 1. Is that is D a subset of A?
No.
Excuse me.
I'd say no because of the 0.
That is exactly correct. How do we say that? We say that like this. D is not a subset of A. So now it's just kind of like, you know, if you want to say not, you just put a slash through. Okay, now, you remember what an empty set is?
With nothing in it.
That's right. So this is, by the way, another symbol for the empty set. This circle with a line through it. So this says the empty set is a subset of A. Now, on the next slide, by the way, this is true. The empty set is a subset of A. In fact, this is something you should definitely write down, this statement at the top with the red asterisk. The empty set is a subset of every set, even itself. So if anybody asks you, is the empty set a subset of that? You would automatically say yes. The empty set is a subset of every set, even itself. Now, next, we have something called an improper subset. So the word subset kind of implies what? The word sub means like part of, right? Sub, subheading, underneath, part of. And so this is called an improper subset. Why is it A is an improper subset of set A? And you notice we have a new symbol. We have the horseshoe with a line under it.
Mm-hmm.
And that line kind of indicates, oh, they're equal, they're the same. So we call that an improper subset because is it really any sub? Is A actually a sub of A? No, they're equal. So that's what we mean by an improper subset. Every other kind of subset is called proper. And then on the bottom, when you see a script U like that, that stands for something called the universal set. You'll see we're going to be doing examples with that in it. Okay. Mm-hmm. So here's an example, and what we got this funny looking. This is like a horseshoe with a slash in the middle. That funny looking E stands for is an element of. Is an element of. And I've got some examples of that on this page. I made an example set of set A. Set A has the numbers 1, 2, 3, and 4 in it. What do you think about that first statement? Is 1 an element of A?
Yes.
Yep. Is 2 an element of A? Yep. 3 is an element of A. 4 is an element of A. Is 5 an element of A?
No.
No. And so do you see how I wrote 5 is not an element of A? There's that slash meaning not again. And just to practice a little bit, way at the bottom of the page, the set with 1 and 2 in it, what do you think? Is that a subset of A?
Yeah.
Yes, because 1 and 2 are also elements of set A. Okay, makes sense?
Yep.
Yes. Were you asking? No, you're not asking a question. Okay.
No.
So now comes, as you can tell, this page is all about figuring out how many subsets does a set have. All right. So what I did is I did 3 examples on this page. So if you go to the left, you'll see I have this little A1. I don't know, it's just what I call the first set. Set A1 has just 1 element in it. 1. Okay? Let's see if we can write down all of the subsets of set A1. Are you remembering that the empty set could be a subset of every set? So you see I have the empty set listed here, and this set with 1 in it. So how many subsets does set A have?
2.
Correct. So let's just, here we're doing pattern matching here. So when a set has 1 element, as Marilyn said, it has 2 subsets. So we're gonna find patterns a lot like we did last time. All right, here's set A2. Set A2 has 2 elements, letters in this case, A and B. What are all the subsets? Well, you could have the set with A in it, you could have the set with B in it, you could have the set with A and B in it, and you could have the empty set. By the way, is this, what special kind of subset is this one? You remember?
Yeah.
Proper? No, not improper.
That's right. Yeah. Non-proper or improper. Good. Good job.
Okay.
Okay. So how many elements does set A2 have? It has 2 elements. How many subsets do we have listed?
4.
1, 2, 3, 4. We got 4 of them. Okay. Now let's do set A3. Set 3 has 3 elements, and they are circle, triangle, square. That's kind of sloppy, but that's what that's supposed to read. Circle, triangle, square. What are all the subsets? Well, first you got your singles. You got a circle, you got a set with a triangle in it, you got a set with a square in it. Then you got all your what? All your so-called doubles. Circle, triangle, circle, square, triangle, square. And then finally you got the identical set, circle, triangle, square. Oh, and don't forget the empty set. How many subsets do we have there?
Nine.
1, 2, 3. Here, I'll count them. 1. Whoop. Got to grab my pen. Sorry. 1, 2, 3, 4, 5, 6, 7, 8.
8. Okay.
Okay, now I don't know if you can tell the pattern here. The pattern is what? As we move down, each time the number is doubled, right? You see that? 2 doubled is 4, 4 doubled is 8. Actually, the formula is 2 to the nth power. What do I mean by n? If you look up here, N is how many elements the original set had. So, for example, in set A1, it would be 2 to the 1 power. And 2 to the 1 power is 2. Oh, yeah, that's what we got. In set 2, it's 2 to the 2 power. 2 squared is 4. And in set 3, it's 2 to the 3. 2 times 2 times 2 is 8. So here is the way to figure out, right down here. Oh, I lost my pen. Anyway, down here is the way, this is the formula for finding how many subsets a set has. So, you guys, you guys all have, you've all heard of Baskin Robbins ice cream, right?
Yes.
Yeah.
And what do they have on their sign? Anybody remember? I think it says 31 flavors.
Yeah.
I don't think they've changed that. Okay. Well, how do they come up with that? Well, it's actually 2 to the 5 power. Okay. So, I don't know what the flavors are. You got probably vanilla, chocolate, strawberry, whatever the 5 base. They've got 5 basic flavors. What are the rest of them? They're all combinations. Okay. So I want vanilla with strawberry. Okay. So they're all subsets. Okay. What's 2 to the 5 power? Well, that'd be 2 times 2, which is 4, times the third one, times the third one. 4 times 2 is 8. A fourth one, 8 times 2 is 16. A fifth one, 16 times 2 is 32. Well, I thought they only had 31 flavors. They do. That's because who in the world is going to want to buy an empty set? Yeah, I'd like a cone that has no ice cream in it. I don't think anybody's going to do that. But actually, so really, Baskin Robbins is based on, if they would just add one more flavor, they could go up to 63. Because 32 doubled is 64. If they had 2 more, if they had 2 more flavors, my goodness, they're up to 120. You see how they can. But anyway, that's where they decided we're only going to have 5 basic flavors. Okay. So this page, the whole idea is, how does one figure out how many subsets a set has? Answer: find out how many elements the set has, n, and then take 2 to the n power. How do you actually list them all out? Well, we've got some examples here. You're going to have to provide some too, but don't forget the empty set and the improper subset, the one that's got everything in it. Okay. All right. So here's a problem from the assignment. It's a little bit ahead of time, but if you look, I don't know if you have your books handy.
Yeah.
Yeah.
But if you look at number 67, it's on page 62. Okay, so number 67 says if A is the set of numbers that are divisible by 2. So I started writing them out. What are the numbers divisible by 2? 0, 2, 4, 6, 8, 10. It's basically just all the even numbers, right? Okay. Set B is a set of numbers that are divisible by 4. And they are 0,
4, 8.
8, 12, 16, yeah. So now, at the bottom, I've already got it answered, but the question is A a subset of B? So in other words, are all the elements in A in set B?
Yes.
Is there a 2 in set B?
Oh.
No.
So because not all the elements of A are in set B, you would have to say, no, A is not a subset of B.
Okay.
And now on the right side, is B a subset of A? So you got to think ahead now. Are the numbers in set B, are they in set A, even though I don't have all of A written out?
Mm-hmm.
It is, isn't it? Do you see? Is there an 8 in set A? Yeah, 0, 2, 4, 6, 8. So that one is true. Yes, B is a subset of A. I think that's one of your assigned problems. So you better get that one right. That was not a threat. That was a joke. Okay. All right, let's go. So here's what the assignment has in it. I've got a little bit more to show you, but anyway, let you write this down. 1 to 71, the odd numbered problems. And I've got some, I want you to do the even, just some evens too, 10, 12, and 14. Okay? So 1 to 71 odds, and then do 10, 12, and 14.
Does the 10 through 14, that's not extra credit, right? Because you're assigning that?
No, it's just part of the assignment. And you're right, that's not in the book. But yeah, anyway. I don't usually do very many evens, but anyway. So Mr. Kirchner was here for a very short time and left. I certainly hope I didn't drive him away. Yeah. So is there anything you would like a repeat on, or me to go a little bit slower on? That's basically this last, the lesson that, the extra lesson we were going to do on today's session.
Okay, I have a question, and it may sound maybe kind of elementary, but
elementary is fine.
It was that one that I was asking about. I guess I see where I got it wrong, because I guess I didn't understand what cubing a cube was.
Oh,
so, 35 and number 35. So I'm thinking 1 cubed was 3. So
yeah, you would have to know what that. You're right. Anyway, whenever there's a little number raised up like that, it means multiply it that many times.
So 5 times 3.
So 5 to the 3 power means 5 times 5 times 5.
Okay.
3 times. And 3 to the 4 power means 3 times 3 times 3 times 3. Mm-hmm. So that upper little number is simply how many times you multiply.
Okay.
Yeah, that would definitely be a hindrance when you're doing a problem like this.
Got it.
Boy, that would definitely stop you. Any other questions you would like to ask? So
I do. So for the exercise, I'm actually looking at exercise 2.1.
Yes.
So it says in problems 1 through 8, which of the description defines a set? So like, what do they mean?
Yeah, we didn't talk about that as much. Thank you.
Sure. Because it just says grouchy people, and I mean, I don't really know what that means.
Well, that's the problem.
Okay.
So I would say that's not a set because you have to define the grouchy people.
Yeah, but thank you for bringing that up because we did. Somehow I passed by. We were supposed to talk about that. Yeah, what's a grouchy person? I mean, that's way too nebulous. It's not defined very well at all. So that's the problem. That's not a set because to one person, a guy might be grumpy. To another person, he might be pleasant. You know.
But do we just put like number one, like grouchy people is a problem? Equals problem? Like, is that what you want us to do?
You would say, well, I would just answer it, not a set. No.
Not a set. Okay. Okay.
And number two, good tennis players in the United States. What do you think about that one?
Not a set.
Yeah, what in the world is good? You could say, well, one who's won at least a dozen matches. Okay, that I can check. How about number three, retired baseball players with a lifetime batting average of 400 or better?
Yeah.
That's a set.
That's a set. Yep. How about number four, students taking math courses at Yale University at the present moment?
Not a set.
A set.
Oh, wait, maybe yes, you're right.
I mean, if we went to Yale right now and said, could you give us a list of all the people taking math courses right now? I think that's a set.
Yeah, that's a set. Okay.
So anyway, thank you for asking that question because
sure.
That's the only thing you're looking for. Is it well defined?
Mm-hmm.
And if there's any doubt, like the set of all nice days in Wisconsin. It might be an
empty set,
right? but there might be some guy here from Nome who thinks this is like going to Florida, and he's out in the backyard right now, sunning himself. Well, not right now; it's a little bit dark, but that is so. Yeah, I mean, each person has a different perspective, So yeah, you get the idea. So you could just say yes or no on that. That would be fine.
Okay.
Do you see any other parts on the assignment we want to talk about? Oh, I got one comment. Take a look at number 14 for a second. It says in problems 10 through 14, set X is the set with A, B, X, and Y. Fill in the blank with either is an element or is not an element to make the statement correct. Okay, that number 14 is really it's not a fair question. I mean, if that was B, comma A, comma Y, then it would be an element. But the word. So I'm just telling you right now, that one's not an element. It's kind of I shouldn't have picked that one. Likewise, they do the same thing in the next part. Well, no, never mind.
Real quick, just so I understand. So back to like the number one. So like the ones where we have to answer yes or no.
Yes.
So like for number 5, it says X, and
all
then
X such that X is a counting number.
Yeah, X and X is an odd counting number.
Yeah, that X/X stands for all X such that X. All X such that X is an odd counting number. What do you think? Is that well defined? Is that a set? Counting numbers just means 1, 2, 3, 4, 5, and an odd one would just mean what? 1, 3, 5,
7.
So that's pretty well that's well defined.
Mm-hmm.
Okay.
Okay.
No, that's odd notation, but all that x/x means is all x such that x.
Is a counting.
Mathematicians are famous for coming up with shortcuts. So they didn't have to write all those words out. They came up with that symbol.
Okay.
Okay.
All right. Well, I think we're going to be all set until next Wednesday. I will see you then. Thank you for being here.
Thank you.
Thank you.
Good night.
Good night.
Night.